38 million tons of dense, slimy, rotten egg-smelling invasive biomass are spreading across Caribbean shorelines like a living tide, stretching thousands of kilometers. Sargassum not only buries beaches, suffocates coral reefs, and chokes seagrass, the lungs of shallow waters, but also turns tourist paradises into massive zones of organic decay. This issue goes far beyond a scenic disaster. For destinations like Barbados, Jamaica, the Dominican Republic, and Mexico's coastline, it is a direct blow to the tourism industry, the engine that generates tens of billions of dollars each year. So what if sargassum is not waste, but a raw material? What if the very thing paralyzing coastlines could become construction bricks, fuel, high-tech materials, and even wearable fibers instead? This is not just a story about cleaning up a biological disaster, but about reversing an entire value chain. And the journey of turning an invasive seaweed surge into an industrial resource begins right now. To understand why that question is serious, we need to look at the true scale of the problem. Since 2011, hundreds of millions of tons of sargassum have washed ashore across the Caribbean and Mexico. The year 2025 alone has recorded one of the largest outbreaks ever measured, with about 38 million tons appearing in May alone. Satellite models show a seaweed belt stretching thousands of kilometers across the Atlantic, a floating river of biomass on the ocean surface. This turns sargassum handling into a massive logistics problem, comparable to national-scale urban and ocean waste collection campaigns that the United States and several countries, such as Indonesia and the Philippines, have failed to control when attempting to operate at full scale. The economic impact is visible enough that many coastal hotels have seen occupancy rates drop by about 10% during peak seaweed season alone. The cost of clearing just 1 kilometer of beachfront can reach $70,000 per month, not including transport and final disposal. Much of the collected biomass cannot be sent to standard landfills because it is too wet and too saline, leading to temporary dumping sites that create secondary pollution. In 2022, the U.S. Virgin Islands had to declare a state of emergency when seaweed clogged the intake system of a desalination plant, meaning this biomass affects not only tourism but also freshwater security. At the ecological level, thick seaweed mats block shallow waters, cut off sunlight, kill seagrass, weaken coral, and collapse food chains. Juvenile fish lose shelter and local fisheries are affected. When these pieces are put together, the picture is no longer unusually high seaweed, but a new natural system colliding directly with the coastal economic system. And when two systems collide, understanding how it operates becomes the necessary next step. Sargassum differs from most familiar seaweeds in one crucial way. It does not need to anchor to the seafloor. Along its body are small air bladders that allow the entire structure to float permanently on the ocean surface. It does not reproduce by seeds and does not require a complex cycle. It only needs to break into fragments, and each fragment continues to grow like an alien organism split in two in science fiction films. The more we cut it, the more it multiplies. This replication mechanism makes it one of the fastest self-copying biomass systems in nature, with a spread rate that can be roughly 10 to 50 times higher than a typical plant population under equivalent conditions. For centuries, this was not a problem and drew little attention because sargassum was kept stable within the Sargasso Sea, a massive ocean gyre that acts like a natural trap, holding the seaweed in a closed circulation loop, like a whirlpool with no exit. The breaking point came around 2010, when an unusual atmospheric and current event pushed part of the seaweed mass out of that gyre system. Once it escaped into the open ocean, it encountered more favorable conditions: warmer water, nutrient flows from major rivers, and rising surface temperatures. The result was a new Sargassum belt stretching thousands of kilometers across the Atlantic, drifting seasonally and persistently returning to the Caribbean each year. And that is only the visible part of the problem. What matters is this is not a random recurring event. It is a new system equilibrium. When a new equilibrium emerges, the effective strategy is not to fight it completely, but to learn how to reuse that material flow. In other words, if we cannot stop it from arriving, we have to decide what to do with it when it does. One of the first people to choose that approach was Omar Vasquez in Yucatan. Instead of seeing Sargassum as a cleanup cost, he viewed it as a material component. He began experimenting with pressing treated seaweed into construction bricks at a ratio of about 40%. The idea sounded simple, but the reality was full of friction. Early test batches cracked due to salt crystallization. High moisture reduced compressive strength. Residual organic odor triggered community opposition. Building standards had no evaluation framework for seaweed bricks. The project nearly stopped several times. After many rounds of salt washing, blending, and layered pressing, the team produced bricks durable enough for real use. The first house built with Sargassum bricks in 2018 went through 5 hurricanes without structural failure. Production costs were about $0.10 to 25 cents lower per brick than traditional bricks based on field trials, and residents reported indoor temperatures could be about 2 to 4 degrees Celsius cooler during peak heat. A side benefit from the organic fiber structure and the material's lower thermal conductivity. A single such house can lock away about 20 tons of what was once waste biomass. However, even this model is not a complete solution, because construction can only absorb a small fraction of the seaweed that washes ashore each year. That leads to the next question in the value chain. If not only building materials, could we extract energy directly from its decomposition process instead? If bricks lock biomass into a solid structure, the next direction is to extract energy directly from its decomposition process. When Sargassum decays, it always produces methane, whether on the beach, in a landfill, or inside a digester. Chemically, that is fuel. The only difference is whether humans capture it or let it escape into the atmosphere. On the island of Grenada, a startup group led by Benjamin Nestorovic chose the capture approach. They built a biodigester system that feeds Sargassum mixed with food waste and livestock manure to grow methane-producing microbial communities, then clean and compress the gas for direct use. The first batches failed because high salinity collapsed the microbial population, and gas output was low and unstable. It took multiple rounds of dilution adjustment and pH and temperature control before the system reached continuous operating stability. The biogas produced is now sufficient to supply an industrial kitchen at a local food processing facility, and the project is expanding to a 150 kilowatt power generator with the capacity to process 8,000 tons of seaweed per year, roughly equivalent to the output of about 1,500 residential solar panels at average capacity, but with the advantage of not depending on sunlight and running at night. For islands that must import expensive diesel, even cutting 0.5% of peak load has meaningful financial and emissions impact. But energy is only the lowest value layer of this biomass. At the same time, this model still faces supply chain challenges. Collecting, transporting, and pre-processing wet seaweed is costly. That is pushing a more ambitious direction, upgrading methane into transportation fuel, where the value per unit of energy is higher. Another research branch in Barbados has experimented with fermenting Sargassum using wastewater from rum distilleries and local sheep manure to produce biomethane pure enough for internal combustion engines after a rapid retrofit, costing about $2,500 and 4 hours of technical work. The vehicle runs, but the commercialization challenge depends on a gas compression and distribution network, an infrastructure that is not easy to build on small islands. This infrastructure bottleneck has pushed many groups to change direction. Instead of burning biomass for low-value energy, they refine it to obtain high-value molecules. Sargassum contains alginate and fucoidan, natural polymers with water retention, thickening, and film-forming properties, used in cosmetics, pharmaceuticals, and textile printing. The value per kilogram is many times higher than fuel. But this is not a frictionless miracle. Sargassum often absorbs arsenic and heavy metals from seawater, forcing the process to include complex detoxification steps, increasing costs and requiring strict control. Ironically, this technical barrier becomes a competitive advantage. When refining technology is good enough to remove toxins, the output products become reliable and difficult to replicate. From the molecular level, the value chain continues to climb to the structural level, where fibers and plastic replacement materials begin to emerge. Many young companies are extracting fibers from sargassum, combined with agricultural byproducts such as banana stems and pineapple leaves, to produce grease-resistant and water-resistant paper and food packaging, targeting directly the single-use plastic replacement market. The process is not simple. Seaweed fibers are short, uneven, and prone to decay, requiring mechanical and chemical treatment to increase strength and bonding capacity. Some material lines have already achieved pilot-scale sheet formation and fiber spinning, opening the path toward lightweight bio-based textiles. But the bigger technological leap lies in nanocellulose, nanoscale fibers that occur naturally in plant and seaweed cell walls. In strength-to-weight ratio, it can rival steel, acting like invisible reinforcement when mixed into plastics, paints, and adhesives. Technology groups in the United States have developed bio-based solvent processes to extract and cut seaweed fibers down to hundreds of nanometers in size, then tune their surface charge to create additives for composites and bonding coatings. Industrial-scale tests show that seaweed-based nanocellulose coatings can reinforce the surface of carbon fiber, a core material in aerospace and high-performance sports. But the energy cost of nanoprocessing remains a barrier, and many batches have not yet reached the required uniformity. This is the familiar valley of death of new materials, where many good ideas stop before crossing the economic threshold. To get through it requires not only startups, but also foundational research, and that is where the scientific climax begins. Research funding programs worth tens of millions of dollars are now focused on turning sargassum into a multi-output chemical platform. Laboratories are analyzing compounds produced during fermentation and reprogramming microbes to increase yields of high-value chemicals. Other groups are optimizing bacterial strains that produce the most methane-rich biogas. A more ambitious pathway converts complex seaweed sugars into hydrogen through a thermocatalytic process at around 500 degrees Celsius with alkali and nickel, producing high-purity hydrogen along with sodium carbonate as a byproduct. That byproduct can then enter molten salt electrolysis processes, from the same technology family used to refine aluminum, to recover trace metals and even synthesize nanocarbon structures. When these pieces are assembled, a new industrial architecture emerges, collecting drifting biomass, pre-processing, detoxifying, molecular separation, and upgrading into fuels, polymers, nanofibers, and reinforcement materials. A value chain that does not begin with mines or oil wells, but with a seasonal, floating material stream. Challenges remain: logistics costs, supply variability, quality standardization, but the direction is clear. Shifting from a waste removal model to a distributed resource extraction model. Sargassum landfalls may still be an ecological disaster at the starting point, but at the end point, they could become a foundation for next-generation materials and energy. The question is no longer how much we can remove, but how intelligently we can extract value. And if this model proves effective in the Caribbean, it could become a template for how the world handles other large-scale biological waste streams in the future. From algal blooms to agricultural residues. If you were the mayor of a coastal city, what decision would you make when faced with 38 million tons of sargassum? And which application do you think has the strongest real scaling potential? Energy, materials, or high-value chemicals? Write your choice and your reasoning in the comments.